Given the graph of f of x, sketch an approximate graph of f prime of x, its derivative. So remember that f of x has the input of x, and f prime of x also has the input of x, but its output is whatever the slope is at x. First, I'm going to look for all turning points, maxima, minima, anytime the tangent line might be 0, etc. So I see that this is a parabola. Parabolas are symmetrical. The line of symmetry for this one looks to be like it's at 1, which means that its vertex is at x equals 1, and there's a horizontal tangent line there at the vertex because that's a minimum. So we're going to make a table, and the first value of x that I want to put on there is 1. Okay, in fact, I want that to be the middle value because everything is centering around 1, the axis of symmetry. So from there, I'm going to just estimate maybe 0 and 2, and then maybe go one more unit, so to -1 and to +3. So at 1, the slope is 0. That is the minimum of the graph. And then I will look at what is happening at 0. So at 0, here is the point, and the tangent line looks like its slope is probably -1. I'll put that as -1. The nice thing about that is that since a parabola is symmetrical, I can estimate that the slope at 2 is +1. So just the positive version of the slope on the other side. And then when you plug in -1, it looks kind of like your slope is -2, I feel like. You can kind of do a little slope triangle, just check it out. Again, these are estimations, okay? You estimate what your slope is. And on the other side, your slope would be approximately +1/2 because this is a positive slope. Sorry, +2 because this is a positive slope. Okay, and now I think we have enough points to actually give a good estimate of what the derivative looks like. So -1, -2. Go ahead and plot these points. And you have a line, which we learned before. Yeah, the derivative of a parabola is a line. Okay, so we have a rational function, and it appears to have some sort of vertical asymptote in here. Okay, so I'm going to try to figure out where exactly that is. Please remember that the branches of your rational function are equidistant from the vertical asymptote, so that should be able to help us, or it's like they're reflected kind of over like this diagonal line, if you remember. So I estimated that the vertical asymptote would be at -3 or -4. Because this branch is so far away, I'm guessing it's not at -4. I'm guessing this one would just keep going. We're just not seeing the full thing. So I'm going to estimate that it's at -3. Okay, that is my vertical asymptote. Lovely. Everything is kind of centering around that vertical asymptote. So we're going to put that in the middle, -3. We're going to need to kind of estimate a few more points than we did in the previous graph because more stuff is happening here. So the slope is, well, literally the output is an asymptote, so the slope of an asymptote is definitely undefined. The limit does not exist, so the derivative there does not exist. Now I look for any other points that might be helpful, right? We usually would look for whenever the derivative was 0, like maxima or minima. But here we're going to need to plug in a few more values and kind of estimate. So the first thing I look for is just anything that might be an easy estimate. And what I would consider an easy estimate would be something like at x equals 0, where it really looks like the slope is just -1, okay? And if the slope is -1 here, we look at this point, remember, reflected, not over the asymptote, but it's some sort of a reflection. And this one would be -1 as well, okay? So that is 0, -6. The slopes there are -1. We can even start graphing before we find all of the points that we want to. So at -3, we have an undefined slope, so another vertical asymptote. And then at -6, we're at -1. And at 0, we're at -1. So we want to know what is happening as we get closer to the vertical asymptote, and then what's happening as we get further from the vertical asymptote. Then we should have a complete graph. So I'm going to plug in -5. -5 is right here, and I estimated the slope of -5 to be approximately up 3/1, but in the negative direction, so down 3/1, so -3. That was my estimate for -5, was that we had a slope of -3. Now, you're also going to have a slope of -3 on this branch in a very similar position. Okay, so if we had plugged in -5 and got a slope of -3, that was 2 units away from the vertical asymptote. So I'm going to go 2 units away from the vertical asymptote. That would be -1. And then go ahead and check. Is the slope at -1, does it appear to be -3? Yeah, that looks to be about -3 to me. So that also gives me a little bit of a clearer picture. Let's plot those points over here. So we appear to be going down as we approach the vertical asymptote of the derivative. Let's see what's happening as we move away from that vertical asymptote. So the last things I'm going to plug in would be -7 and 1. -7 is approximately here. And I estimated that the slope of -7, the slope at -7 was approximately -1/2. Which means the slope at 1 would be also approximately 1/2, because it is the same distance away from the vertical asymptote. So we're centering everything around the vertical asymptote. So -1/2 and -1/2. So I know this is going down, I know this is going down, I know the other one is going up. Does it ever cross the x-axis and head into the positive direction? Well, let's take a look. As we get further and further away from the vertical asymptote, we get closer and closer to what looks like almost horizontal lines, so possibly a slope of 0, like we're approaching a slope of 0, but it does not appear as though this branch is going to just pop back up, okay, and become a positive slope. So there's probably a horizontal asymptote of some type stopping us from going above 0 for the derivative. After doing number 2, number 3 might be a little bit easier for you to understand. So I'm going to go through it a little bit faster. Try it on your own though first before you watch me do it. The vertical asymptote here is at -1. It may appear as though this graph just kind of stops. No, it does not stop. It's continuing to go on. It just, the pixels can't get as small as it needs to be truly be accurate. So we have a vertical asymptote at -1. That means everything, all the points that I plug in or that I estimate are going to center around -1. So we'll put -1 in the middle, and that gives me an undefined slope. As we move from -1, there is kind of there's definitely a change happening here, right? We have a negative slope, a negative slope, a negative slope, a zero slope, a positive slope, a positive slope, a positive slope. Okay, so there is a complete change in direction from negative to positive as we move away from the vertical asymptote. So I believe my estimate for where 0 is at approximately -2. So at approximately -2, I have a slope of 0, which would mean that at approximately 0, I also have a slope of 0. I'm going to need to do some sort of a decimal estimate though because of this quick turn that this branch takes. At -1.5, I estimated that my slope was approximately -3. So that at -0.5, that estimate will be the same, -3. Okay, and as you move away from the asymptote, remember your slopes are going from 0 to positive slopes, 0 slope to positive slopes. I estimated this line, which was like at the point -5 and 3, this kind of tangent line that runs through the whole thing, I estimated the slope of that line was approximately +3. So that at -5, your slope is +3, and at 3, your slope is +3. Go ahead and graph these points. And this one is actually symmetrical about the vertical asymptote. Beautiful. Ooh, what's this craziness? You've got 2 vertical asymptotes. -4 and 4. So this is actually all centering around the y-axis, which helps us. At -4, we need to say that the slope is undefined. At +4, we need to say that the slope is undefined. But we also need to know what the slopes are in between and around these vertical asymptotes. So I'll do the vertical asymptotes on the derivative graph first. My next question is there any place where the slope appears to be 0? And the answer is yes, literally at 0. It's almost like this little thing inside of here is almost as flat as a tabletop. So at 0, we have a slope of 0. So what I did around these values is find one other point. So I did -5. I did halfway in between here, so -2, 2, and 5. Again, you can always just estimate slope being positive, slope being negative. You don't have to estimate specific number slopes, okay? But this helps me personally, so this is how I'm going to do it. -5 has a slope of approximately 1/2, and that's a positive 1/2. But at +5, your slope is -1/2. Now at 2, what do we estimate? I ended up just estimating it was about 1/6. Of course, that would be negative 1/6. And on the other side, this one would be positive 1/6. Go ahead and plot these points. Now you may say to yourself, I still don't know what's going on here. So you could plug in more points, but I'm going to estimate the rest of the way. Okay? From the slope at -5, which I estimated to be -1/2, as you move toward the vertical asymptote, the slopes become larger and larger positive numbers. So as we move toward the asymptote, we're going to go up. As we move away from the vertical asymptote, we end up getting slopes that are smaller numbers, getting closer and closer to 0, but not quite 0. This one is going to be symmetrical in kind of a reflection in that fact. So as we move toward the asymptote, the slopes are getting more and more negative, so smaller and smaller negative numbers. And as you move away from the vertical asymptote, you get closer to 0, but not quite. So inside here, if you have one of these branches is opening up toward the sky, one is opening down, then the middle piece has to be like a cubic wave. And you can see what's happening here. The slopes are more and more and more positive as we get closer to -4. So we go up. The slopes are more and more and more negative as we get closer to +4. Connect the dots and then go down. For number 12, I decided to rewrite the 5th root of x as x to the 1/5 so that I could distribute and hopefully use the power rule instead of needing to use the product rule. So f of x is equal to 4x to the, okay, if you have same base, then you add the exponents. What's 1/5 plus 5? That would be 25/5 plus 1/5. So 26/5 plus 2x to the 5th. Now I have a strange exponent, but I can still use the power rule. So I'm going to evaluate the derivative now. So f prime of x is equal to pop down, power down. 26/5 times 4 is 104/5, and that would be times x to the, you take 26/5 and you subtract 1, or you subtract 5/5, and you get 21/5. So that's our new exponent, plus 10x to the 4th. This is an acceptable answer. I personally think it looks a little cleaner when it's all in the same fraction. So I multiply by 5/5 and end up getting 104x to the 21/5 plus 50 x to the 4th all over 5. Also an acceptable answer. Hey, what if you wrote x to the 21/5? What if you wrote that as 5th root of x to the 21? That's also okay. What if you wrote that as 5th root of x to the 21? That is also an acceptable answer. For number 16, I see that I'll probably use the quotient rule, but then there's an x to the -5 in the denominator. Let's rewrite it as a fraction first of all, and I'll show you why. X to the 5th minus 5/5 plus 1/x to the 5th. before we even derive it, let's get rid of this little mini fraction. So your mini denominator is x to the fifth, and that's the LCD because that's the only denominator we have. So we're going to multiply by x to the fifth over x to the fifth and distribute. Y is equal to x to the 10th minus 5x to the fifth over 5x to the fifth plus 1. Now we have something that's going to be easier to derive. Okay, here's the lower function, and here's the higher function. When I say d, I mean derivative. Low d high minus high d low. Over low squared we go. Over low squared we go. Low d high minus high d low. Over low squared we go. Over low squared we go. Low d high minus high d low. Over low squared we go. So let's continue to derive. 5x to the fifth plus 1 times the power rule, pop down, power down, 10x to the ninth minus 25x to the fourth minus this quantity being multiplied by the derivative of 5x to the fifth, which is 25x to the fourth plus 0 over low squared we go. Go ahead and distribute, see if we can combine any like terms and reduce. So we have 50x to the 14 minus 125x to the 9 plus 10x to the 9 minus 25x to the fourth. I'm going to change this to addition and just put the negative here so that I just distribute the negative and the 25x to the fourth all at once. So this would be negative 25x to the fourth times x to the 10th, which would be negative 25x to the 14th, plus 125x to the 5 plus 4 is 9. We do have some like terms. We have some 14s and some 9s. So y prime is equal to 25x to the 14th. That's 0, so plus 10x to the 9 minus 25x to the 4th. 5x to the 5th plus 1 squared. Now, at this point in time, you're not done if you can reduce something inside here. So I see, oh, 5 goes into this, 5 goes into that, 5 goes into this, 5 goes into this. Oh, 5, is 5 going to go into this when you multiply it out? Just to be sure, let's try it out. That would be 25x to the 10th plus 10x to the 5th plus 1. Okay, so it does not reduce. You don't have to expand, but you do if you need to check if you can reduce. So if you can't see immediately if it's reducible or not, then you will need to expand and make sure that you have completely reduced and simplified it all the way. So both of these would be acceptable answers on the quiz. The last problem I'm going to do is number 17. For each of these, find the points where the tangent line to the function is horizontal. When the tangent line is horizontal, that means the derivative is 0. or the slope is 0. So we need to find the points where the slope is 0 or the derivative is 0. So first we're going to find the derivative, then we're going to find the x values, and then we're going to find the y values to complete the point. So y prime, we will use the power rule, negative 3x squared plus 8x to the 1. Here's the derivative. Now, to find the x values of the function where the tangent line is horizontal, I will replace y prime with 0, because when the slope of the line is 0, when the slope of the tangent is 0, then you have a horizontal tangent line. I'm going to factor out a negative x. This is 3x minus 8. Use zero product property to find the values for x. So negative x is equal to 0, meaning 0 is one of my x values where the tangent line is 0. 3x minus 8 equals 0, so add 8 on both sides and divide by 3. X is equal to 8 over 3. These are the x values. You're not done. They said find the points, so you need to plug it in to find the y value. Plug it in where? Into the original function. So when you plug in 0 into the original function, you get negative 0 cubed plus 4 times 0 squared minus 6. Okay, so the y that goes along with 0 is negative 6. That one's pretty easy. The other one is a little bit trickier. So negative 8 thirds cubed plus 4 times 8 thirds squared minus 6. Plug it into a calculator and you end up getting 94 over 27. 8 over 3, 94 over 27. If you use decimals, make sure you don't round, so please just leave as fractions. And these are your points where the tangent line is 0, horizontal.